Okay, so I'm going to present sort of joint work with Altmejd at Stockholm University and something finance, something at economics, and Joacim Rocklöv, who is at Umeå University. And it's about COVID nowcasting, where now also represent that we're not doing forecasting, but we're actually just predicting the current day and past day. So that's why it's called nowcasting, apparently. I did not know this word until I did this work, so I called it forecasting earlier. And yes, if there are questions, please just interrupt, because it's preferable that people ask questions during the talk than after, especially since I tend to speed up if nobody asks me questions. So there will be probably less explanation the less questions you ask on your own. Anyways, so all right. You want just a quick, I keep seeing these mentions in the letting people in. So, yeah, so I'm going to talk about nowcasting and sort of how to predict number of deaths of COVID with what information we have so far, and what that on a specific day. So the issue of what we're trying to predict is that at a given day, we typically don't know until much later, several days, and in Sweden actually a few weeks, how many people actually died on that given day. Because on the given day, the number of people who died with COVID is not yet reported. So therefore, as the time goes on, we will get more information about the specific day. But to sort of, the reason why this is sort of interesting is, of course, it's a good way to measure or get an understanding of where the pandemic is going, because unlike, hopefully at least, unlike sort of predictions where you have number of infected and so on, this typically depends very heavily on how many people you have tested, what cohort you tested, although deaths sort of have a similar problem with because of the age dynamic of people dying with COVID. It's more stable, at least in theory, than number of predictions. So it's sort of important value to have current information about. So in data for Sweden and UK, the data is presented before it's fully collected. So we will sort of hear numbers that are not complete yet. So we will sort of know how many that are known to be dead, say today, but we will know that the number will increase in a couple of days. And the reason why I started looking for this was at when we looked at our Folkhälsomyndigheten or Department of Health, not exactly, they were reporting results like this. And what they were using was this moving average, or 7-day moving average. And in fact, here in the beginning, they actually just used the 7-day moving average. But here, as you can see, they actually moved back. So they only presented for 10 days in the past, the 7-day moving average. And the reason for this is that they noticed that this was very biased. But still here we have bias. And the issue is that when the data is being collected so that there is most biased most recently and less bias in the end, this causes a trend by itself, right? Because we have not reported here, so it looks like there's a downward curve here. It might be, and I think it was a bit going down here, but it's much less than it looks because we have not yet gotten the reporting. So this gives you sort of a false impression that there is a downward trend where it might not be. In fact, it might be upwards. So that's why I was sort of looking into this problem. And in fact, it reminded me of some earlier work I did. So I'm going to go and present sort of from where I got the methodology that I used for this paper. But before, I will sort of set up some structure. So the goal of the model is to predict how many died on a given day. Therefore, we denote number of deaths at day t as DAT. But what we actually observe is how many reported deaths on a given day. So rep T represents how many individuals are reported dead on day T reported at day K. I will sort of make it more clear in a data example to make it more easy to say. So let's look at, for instance, in Sweden, 19th of May, 2020. Then, so T is this 19th of May, 2020. K, the report date. So here's a type, no, here's right. At report date, the same as the day of death. We had no reports. So no one was reported dead on 19th of May, on the 19th of May. The next day, the 20th of May, T plus 1, K equals T plus 1, we reported 5 new cases. And the following day, we had 5 minus 12, which are 7. Yes, my subtraction is correct. Day, and 0 the following day. And we continued on so. And slowly the numbers were dropping in so that we can see after 349 days, there are 55 reported that day. But notice here that you had sort of only 0 the first, 5 the second, and 12 the third. So it was far from sort of stable here. Even after 4 days, you're far from the 55, which was the total number.
So I want to understand this better. Yeah. So this is reports on the specific day, how many died.
On the 19th.
Exactly. So all these reports are about this specific day.
Yes.
Yeah. And I noticed this, or yeah, I understand this.
Yeah, precisely.
And now we are showing us the result almost 1 year after the day. So like the 55, like what is the time span where most of the deaths are reported? So this is really like half a year or?
No. I just said that sort of. We'll basically in Sweden, and this we will use, you know that at least after 20-25 days, you are certain. There would be not very few more, maybe 1 or 2. And in UK, you can say like in 8-9 days, they're done. Maybe 10.
Thank you.
So there is a large difference in reporting. Yeah. So we will do this for each day, for each report day and for each backwards prediction day. So that's what we're trying to do. Okay. But this type of data reminded me of work I did a long time ago before I was a PhD student. And I was working before when I was still studying statistics, but very long time ago anyways. Well, I was working on estimated population of natterjack toads in the the coast of Bohuslän. And this was sort of joint work at my father's company, where we sort of tried to estimate the population size of these natterjack toads, which are a red listed species in Sweden, but they are present in Bohuslän. And estimation of populations is well studied in ecology. Typically, one are using what is known as capture-recapture methods. And I will try to sort of, this is sort of the foundation we used to build the model we have for the data. But I will go through now how I did it for this lumber natterjack toad. The issue is when you're sort of trying to estimate population size is that you see a number of animals, let's call it N, but you don't know how many you didn't see, right? So we have a probability of seeing an animal or not. And if we don't know this probability, we cannot get the small n number of catches or how many animals we saw, we cannot relate that to the actually population we're interested in. But if we knew P, it would be approximately that the population should be something like, that's the wrong order, n divided by P. So we would do that. But the difficult problem in sort of these biological data is that you don't have an estimate of P. It's very hard to get. Now, typically this is what's done in capture-recapture method is that you mark the animal somehow, and then you release it, or you mark several animals and release them once you caught them, and then you see what proportion of the marked animals am I able to recapture or see again. That gives us an estimate of P. However, there is a less well-known method known as reaction sampling, which I think is a very bad name, so I keep calling it capture-retain. But the idea there is instead of marking animals, you actually capture them and keep them. And then you go out and capture new animals. And if you have a small population and the size, and you collect a large proportion of the population, this actually will give you this decreasing number that will get fewer and fewer animals, will actually give you an estimate of the probability of catching them, and also the size. And I will go into more details of this. So this is what we actually did for the toads. We collected the toads actually in buckets, because there were small islands, so the population was very reasonable to be closed, or rather closed. So we did this for individual islands. And then you waited a while, and then you went to the same island, say 15 minutes, and collected the same, and collected toads again. And you repeated this 3 times. So we got some observation, how many toads you caught the first time, the second time, and up to the 10th time. And I already said this. And sort of from a mathematical point, with a bit of faith, you could say that catching a toad has a probability P, and the true underlying population is N. So the first batch that you catch, you should catch a binomial distributed number of toads with probability P. But the second time you go out, you already caught the first catch. Therefore, you can't catch them again since we keep them in the bucket. So therefore, this is now the new probability for the second time. And you repeat again the third time. And you see, if this proportion that changes, you will actually get an estimate of what the population should be. And we can therefore jointly estimate both P and N.
I have a question again.
Yes.
So is it reasonable to assume that P is constant, like in each of these trials? This is what you assume, I guess, in your model.
Well, actually, here it actually worked quite well. There are many instances where you can't assume this. And in fact, in our application later on, we will not assume this. Okay. But yes, it is sort of, if there are a group of toads that are better at hiding, then they will have a different probability. Mm-hmm. So we actually did experiments with this where people hid some sort of stones, I don't recall. And it worked horribly for those methods, because the thing is that once you put out the stone and you go back, it's still the stones that were hardest to find that are left. Mm-hmm. Therefore, that probably that it doesn't work, right? So you need sort of some assumption that the population of toads is mixing. But we will see that we can actually later weaken this assumption.
But one could also argue that by reducing the population size, you make it harder to catch it, right?
Yeah. But that's sort of the fundamental thing, right?
No, but even P, I mean, because it's a really hypergeometric distribution, not binomial, and I don't know. I just feel
the key assumption is that each toad at each location is independently easy to capture with the same probability. That is the fundamental assumption. That could definitely be false. Mm-hmm. But here it worked quite well. But and you can do Bayesian estimation and ML estimation, and really don't matter. Well, it matters a lot, but yeah. I realized also while working on this that actually if you do ML, or if you do Bayesian with the uniform priors, there is some clear bias in the sort of the estimation of probabilities and N jointly. But I will not talk about that today and just ignore it. It should not matter for our data in this example, actually, where the COVID is later. But you can easily calculate this bias, and it's not a good thing. But let's see an example instead and ignore this issue. So suppose that we, at the first occasion, captured 22 toads, and the second occasion captured 15 toads. Then the posterior distribution under our assumptions, which can be argued, follows a binomial distribution. So you get n over 22, p to the power of 10 to 1 minus p, n minus 22 for the first batch. And then on the second batch, you get this formula. And here on the right, we see the marginal posterior distributions for the probability P and N. And as we keep on catching toads, you see here 14, and in this case, the true number is 80 and P is 0.3 actually. We keep on getting a posterior distribution, and there we caught 9, now the numbers start dwindling, 7, etc., 6 eventually. We see that we get a rather sharp peak around actually the true value. We underestimate P somewhat. But if we were to continue on ever, in this simulated example, we'd catch the true number of toads. So this is sort of the general idea. And maybe I should say before going back to the COVID data is that, as a funny side note, for this lumberjack toad that we captured, we actually captured more animals than was estimated to exist that was larger than the actual population in Sweden of lumberjacks. So this goes to show that it's very hard to estimate animal populations. So they had no idea. And it's actually questionable that they should be red marked given this, but that report actually suspiciously just disappeared. Yeah, but that's another story. So for the given COVID data, for a given day, we can implement the same idea. We're now, instead of repeated capturing, we think of it as for each day, we get a new vector of observation on how many we can capture. So how many are reported should correspond to a binomial distribution at the first time as number of deaths, the true number following a binomial distribution with some P0. But the difference here, we can of course not report the old cases, so there should be fewer this time in the second case, and so on. And here you can notice that we have this P0, P1, and up to PI, because we will have rather much data, and it's not quite reasonable to assume, and in fact it is not the case, that the P is the same for all. But after a while it seems to stabilize. And I won't go so much into this, but we actually have several days and sort of different P for different weekdays, etc., etc. And I should state here that regarding the nowcasting, that I missed that this actually had been done previously in sort of medical data and so on with delay by Lawless in '94 in Canadian Journal of Statistics. But they in turn actually missed that this had done in biology in 1951 by Moran. So I don't feel as bad as I missed it, given that they missed a sort of huge body of literature also. But never mind that. But this actually was done for medical data here and for rats in 51. But going back to sort of modeling, assumption, and so on. Well, an issue often with binomial or Poisson distribution data is that the data is often more over-dispersed than the actual distribution. So it's higher variability in the data than the distribution allows for. And we will see that this data is no exception. Because sort of, if we have enough data collected, or if we go on log tough, it's kind of reasonable to assume that we actually have the true number of deaths, right? After a while, it doesn't change. So in UK, it should be calculated. This is stable at least after 30 days, most likely much sooner. In that case, we can say that we both have these rep-T, the measurement, the reports, and the actual death. So now it's rather simple to estimate P, right? And let's see an example when we have lag 2, that is the number of cases reported, how many cases are reported 2 days after. Of course, if we go back long enough in history, we actually have this 30, this should be rep, sorry about that. We actually have that the number of deaths should basically be rep here, T30. So we basically have the classical situation of binomial distribution, that this is the number of observation, this is the number of counts. So P2 should basically be this. Is this clear? Yeah. And in that case, given if we sort of say that we know P approximately, here I did it correct, this number should basically follow a binomial distribution with these parameters. And therefore, we can generate confidence intervals around this. And I divide it by dt instead, because then you get the proportion. So we can see how well does our binomial distribution fit our assumption. Let's see here. And this is what we get. So this is data for UK, I should say. And here are the confidence intervals. 95% confidence interval, and each dot marks one of such observation. And the first thing I can point out is that the confidence interval goes like this due to the fact that the number of deaths were increasing here and decreasing here. But what you clearly can see is that, especially when we are middle, the confidence intervals are not sort of related to the data as they should be theoretically. So we have a clear case of overdispersion. And this would be problematic if we sort of let this fly, because we would be much more certain about the data than is really true, and would generate too narrow confidence band on our predictions. So we need to address this.
Sorry, I have a question regarding the formulas. So the numbers in the subscript are like limits of the summation, right? Here.
Yeah, precisely.
Okay.
I think I used 30 days or what we ever had a limit, but so it's not all the data, right? We end up in April here because we don't have access to.
Okay, no. I was referring to the formula. So if there's rep t plus 2, this means there's the number of individuals or fatalities that are reported on day t and on the next day for this day, right?
Yeah, so maybe I actually did the wrong. 1 second, I will go very quickly to see if I actually managed to flip it. No, it's right. TK. So it's number reported at day t divided by 2 days later. So this is the number of cases at day t reported at day 30. Oh, right. Yeah,
up until day 30.
Yeah, it should be a sum there.
Okay.
Yeah, that's my bad. It should be some rep t from t to up to t30. Sorry about that.
So there's the summation limits.
Yeah, exactly. Yeah,
okay.
So thank you very much. Very good. Yeah, so this is horribly wrong, this approximation. But the sum is correct. So it should be a double sum here also. No, there's correct. There should be double. Okay, never mind. The principle is that after a while we have the truth. And we see this. And again, the same error. So very annoying. But instead we use, to account for this overdispersion, we instead use a beta binomial distribution. And the underlying assumption of a beta binomial distribution is that instead of the regular binomial, you assume that the p in your binomial distribution corresponds to a beta distribution. So if you're not familiar, it's a distribution between 0 and 1. So you get the random p, where here mu is the expected value of p and m is a variance parameter, you can say. And then if you simulate the p like this, plug it in here, you get the beta binomial distribution. And in fact, it's still analytical and you can integrate out this p. And then you get, instead of having a binomial here, you get a beta binomial where you have a mean mu, so which basically works as a p, but you also have an m, which is an overdispersion parameter. I should say that there are some issues that are sort of hidden in the beta binomial distribution that I realized that can be problematic, is that the beta distribution contains bimodal distributions, which is typically not what you want, but it's not an issue here, I think, so we will ignore that. And if we look now on the data, I will just do this, and we compare now the confidence bounds using either beta binomial distribution or beta distribution. You see here that we get much better confidence bounds. In fact, they might be a bit too wide, but it's better to be more certain than too little certain here. So we capture this. We see we have these 4 observations here that we can't explain anyway, but that's life. So it's better to have this sort of uncertainty than having this.
This involved estimation of m, right? Also, right?
Yeah, precisely. So we estimate both mu and m. So we both allow for overdispersion and the mean. So this is the UK data, which actually is very nicely collected. Swedish data is a bit more problematic. For instance, in the beginning of the pandemic, you can see the data looked like this, and this is our beta binomial distribution. The issue here is that it's not completely obvious, but you will see it, one can see it if one examines data more, but there is a clear time trend here. So we see that we have a lot of large values here and we get fewer and fewer longer. And this is what happened in the beginning of this first wave, or sort of middle, where we started collecting the data, was that these probabilities of reporting were decreasing. And this is very bad from a predictive standpoint, because basically we can think of our estimate of people who died is the number reported divided by the probability of survey. So if the probability falls, so we will get fewer and fewer reports, our estimate, if we assume the same, that the distribution is stationary, will give us an underestimate. And this is what happened. So while the sort of data was collecting, they were reporting it with longer and longer lags, so fewer and fewer reports, and therefore we get this trend downwards, which was sort of bad for prediction. So in this case, we will ignore this and focus on the second wave. You can sort of estimate it using more advanced method, and we did, but I'm not going to talk about that now, because actually after the second wave, it's rather
but historically speaking, I kind of remember that around these days that you report here last year, first of all, there was some discussion in the news about the way they were reporting this, and it was clear that somehow they changed the way of doing that.
No, they changed the way in July. They switched reporting from every day to every Tuesdays, Thursdays, and something like that. But that was here. We have not gotten any explanation why this behavior. And in fact, if you looked here, that these were sort of where the highest number were, right? So it was big. The biggest pressure on the hospital and healthcare was here. And here was less pressure, but the numbers really dropped. To be honest, I don't know what happened, and we haven't gotten a good explanation from anywhere. But suspicion is that they were sort of more on their toes and reported things more quickly in the beginning, and then they level off. That's my suspicion, but I don't have any sort of evidence in any ways. And but I still haven't got a good explanation. And we talked a little bit to them, but no. There's also a problem in Sweden where you have different regions that carriers seem to report differently frequently and sort of have different standards. So we have an extra variability there. That might be different from UK, but it doesn't explain this, which is sort of in Sweden behavior that changed over time. And also it doesn't fall that the pressure was highest, because the pressure on the healthcare was highest here. And in the end it didn't. So I don't know what it is. All right. So our model is now that the number of repetition here follows this distribution. I introduced the theta beta just to say that we have different parameters for different lags, different weekdays, etc., etc. And
can I just interrupt you and ask you if you ever tried to incorporate the sort of regional level in your model?
What?
If you try to incorporate the
region,
regions,
no,
basically.
We don't have the data on that level of specific, so we don't have it, unfortunately. You could see it in the data that sort of sometimes you got really big jumps, and then you could see that okay, they was reported in Gothenburg or etc. But we can't pinpoint it to the collect date, and they don't want to give this out due to sort of issue of identifiability of the individuals. Was at least sort of this confidential. They don't want it on the data should be on too fine levels.
Right.
But I mean, they might or might not have the data. I don't know.
Right. Yeah, but it's interesting because if you know the pandemic is moving spatially as well, and then that's connected temporally, and then that.
Yeah. I mean, it's a real big issue if you want to model it well, right? Because if different regions have different patterns of reporting, you will see it sort of when it moves, it will change the distribution of the lags. So I mean, if you were to work there and sort of have access to that data, you definitely need to do it. Anyways, so given that, let us see how the look. So we implemented this. We fitted now the data bit using maximum likelihood of all data, and then we fit now the MCMC sampler just on this number of deaths here, which is a fairly easy way to sample. And this is sort of how the results look for this 17th of November 2020, which was just a random data where the pandemic was got. And here the circles here represent the true data here, but we didn't have access here. The dots represent sort of how many was reported at the given day. So at the 17th of November, you could sort of see that this basically was the same, and then you have this data where you see the falling off here. Here is clearly the trend that this data has not been collected yet, and the true data ends up here. And what you can see here is the 90%, I think, or 95% confidence bound. The blue is the upper, red is the lower. And you can sort of look at this and say, okay, at least it captures the upward wave. But I mean, if you look up here, that it should be so, actually I capped it here, but it goes up to 200, something like that, which is sort of unreasonable. And the reason why this sort of is unreasonable is that we have extra information when we look at this type of data, right? The deaths are not unrelated. There is a sort of epidemic going on, a number of infected individuals. So there is dependence. It's not a random number of deaths are not independent. And so this is very clear. We can
could you please explain for a moment what do we see? So we basically observed the data up to the point when the black dots appeared.
Yes, so basically I stopped plotting the black, but you could put all the black dots here. Yeah, so the black dots is the observed data, right? So if we look at 17th of November, for instance, we have no observation that day. So no one was reported to have death on the 17th of November. Yeah.
Okay, so like initially the black dots are almost the same as the circles.
Yeah. So here I didn't plot them out. There was some issue, so I didn't plot them here. But here you see they are the same. So basically we were done with reporting here. But you see here, the closer we get to the current date.
Okay. Because so the black dots are not how many were reported on a given day, but how many were already collected for this day. So they sum up. They sum up everything to the right hand side.
Yeah, precisely.
Okay, good. Thank you.
Yeah, and then the circle. But the issue, of course, is that we have dependence between. You can see sort of that if no way that this dot could be placed here. So clearly we have a temporal dependence, which of course is the pandemic. And we have lots of factors, but basically what we wanted to count basically is perhaps something like, what is the distribution of death given previous death? How do we take this into account? And then given this latent variable, which we can do in many different ways, we have a beta binomial distribution. And there are many ways that we did this. We could sort of, the way we ended up doing is a Gaussian process that I will explain soon. But before that, there are actually many other methods. For instance, we have access through the Socialstyrelsen, access to ICU data, how many are in the hospital, how many are in intensive care in hospital, how many are hospitalized with COVID, and the number of infected in elder care. So if we sort of take these time series, or a smooth version of this, we could just assume that death should follow this as some, say, Poisson distribution, with some parameters we need to estimate, and also a lag, because there is some lag between these effects. And in fact, we actually initially did this in our online prediction using ICU data, which turned out we did a very bad point to choose them, but I will come back to that. And the reason, of course, is that the death here only correlates with these statistics. it's not a causal relation. So the correlation might change over time, and sort of, for instance, how many infected depends on how many tested, etc. So there are a lot of problems here, and we'll see that. So we have this data where we do this, where I first do the smoothing and just do prediction on the number of deaths. And here we have the three sort of models. So we have number of hospitalized, number in ICU, number infected. And then I fit these values and then fit it to this death. So here is sort of in Sweden, second way. And so let's start with the blue line, which is the ICU data. So you can see here that it levels off here. It follows quite nicely here and then levels off here and so forth. There, I think, is basically where we started incorporating this entire model. So it looks perfectly. We say, okay, let's put it in the model. And then, yeah, that happened. And actually, people pointed out to us that you choose a very bad time, because this was actually when they sort of hit the ceiling how many could be inputted into the ICUs. So they clearly started to something happen. So the correlation between death and the number of ICUs leveled off. So this is why you see this effect that it died off there. But of course we could have used, for instance, the number infected with elder care, which has sort of a nice property that you see it's a lag of 14, which means that if we had a number infected with elder care at 14 days ago, we could give a decent prediction on how many will die. But the issue here is the same, that this data is also lagged. So you have a problem that they don't get the data. We talk to the sociologists and don't get the data right away. So we don't know exactly there. You would have the same sort of model fitting problem there. But you could imagine building the same model for number infected in elder care, and then using that output to predict the number of deaths. But we didn't have access to that data at that time, but it is there. And sort of finally, I will sort of point out this is sort of a very positive thing here. You can see that why you see that the correlation here drops off, right, is most likely due to the vaccination. So you see that the number of ICUs goes up, number of infected hospital goes up, while the number of infected elder cares goes down, and also the deaths, right? Earlier, they were strongly connected, while now at the end, the correlation drops off due to the fact of vaccination. So in some sense, this is a very positive figure. But yeah, so here's another reason, right? If you don't take into account the vaccination, you will, and use this covariate, you will get very incorrect predictions. So instead,
sorry, a question.
Yeah.
Each this line was only based on one predictor, right? Or you didn't treat them jointly?
Yeah, I didn't do a joint prediction on them. No. I mean, that you could do also, but the still issue is remaining, right? That you're online predicting, and then the behaviors results. But I mean, if we could perhaps do this and then the COVID data, but also the question is, what time do we get the data incorrect?
Jonas, I have one question.
Sure.
You've mentioned that, for example, we can see that when vaccinated started, the number of hospitalization and ICU is still going up, but the death is going down. But then the number of infected in elder care still is correlated. So is that because that those people don't get vaccinated, or? No,
they get infected, right? They get vaccinated, so they are protected. That's why the number of infected in elder care goes down. Remember that
it's not the death, it's the infected.
Yeah, the deaths are the dots. Sorry, the deaths are the dots. And then there is the prediction model on each, depending on covariate, right?
Yeah, sorry, I got it wrong.
And it should be elder care, so I think it's plus 70 years old. So they were infected much earlier, vaccinated much earlier. So that's what happens. Okay, anyways. So we didn't, in the end, decide to use any of the, well, we did, but we stopped doing any of the covariates, and instead we added a sort of a Gaussian, latent Gaussian process, or if you want to be Scandinavian, a log Gaussian Cox process, which means that we we model the depth as a Poisson distributed with a variable lambda, which is of course the mean, which it follows a log normal distribution like this. And here are the parameters for this. But I was a bit hesitant to do this first. I didn't want to run sort of more advanced MCMC chains, and especially when you have a latent process, which is Gaussian. This has some theoretical problem with MCMC, and I didn't want to see, because we want to generate online algorithm that sort of worked on a homepage right away. I instead decided to do some approximation. Or I was too lazy, it depends on how you see it. But I wanted something that works very quickly. So I wanted to approximate this distribution in some reasonable way. But this is sort of the general.
So what's it in theta GP? What do you have there?
Yeah, so I use from Lund, I use a maternal covariance function. So the theta GP is a range parameter. So how long is the dependence? The smoothness of the process, how differentiable it is. Also the variance of the process.
Okay.
Chris, you're muted.
So this is parameter for covariance.
Yeah.
Thank you.
So I didn't want to forget something. Yeah. So what I did is that I do the classical old school Box-Cox transformation, where I take the square root, which is reasonable because it gives the correct relation between Poisson data and normal data, right? That the variance is proportional to the mean if you do this transformation. And instead I do this sort of approximation here. And I also examined it clearly that the data basically follows this pattern, that the variance of the depth is proportional to to the mean of the number of depth. So this was the first step, which means that I would be able to solve the latent parameters completely analytically. However, the likelihood component is still not feasible. But so what I did instead is that I also approximated this. Here it's more dubious, but seemed to work quite fine, is that I did this latent model here, the simple model, which gave us two wide confidence band. I denote this F simple. I generate MCMC sample for this because this is a very easy algorithm to sample from, or model to sample from, and you can sort of, if you keep this theta BB fixed, you can sort of estimate each T independently of each other. So you can do it parallel, you can do, it's very easy. It's a one-dimensional problem. So what I did then is I approximated this distribution by a normal distribution, where I said that, okay, this posterior distribution here of dt, well, it should be probably be the expected value of the square root of the posterior distribution here and the variance here. So basically, I just take the square root of our posterior distribution, calculate the mean and variance, and say, okay, this is a normal distribution. This is dubious for small sum, for when the number of when dt is small, works fairly well when dt is large. But we are mostly interested when dt is increasing. Okay, so let's see the results, the difference. So to the left, you have this pure model where we had no prior on the number of depths. You look like this. And here is how it looks when you put in the Gaussian prior. So you see here that we are able to remove this extreme confidence band, but still sort of capture the behavior. So this is sort of our prediction. And here you see, because I'm using the square root, and then I'm taking the confidence band with seal and floor, you get this, that it looks like we're always uncertain here, but ignore that. And this is sort of what is relevant here, right?
So have you looked at this even further, or this is all what you looked at? Like, because it ends in November. So
no. Yeah, I just took one example for Sweden. I will show later.
Yeah. I just wonder if because definitely this number of deaths is going to fall down. So
Yeah.
I hope you will be able to catch it as well.
Exactly. Actually, not perfectly, and this is what I'm going to talk about next. So here is the UK data, and here is sort of the process we see from September. We have all the data from the UK that we were able to get. You can basically see that the process here is a smoothly varying process, right? There is no sudden shifts, etc. So it's rather a smooth process. So in that case, sort of, since we fit this Gaussian process on this model, we get a smooth process. I think it's like, we estimate it to be 3 times differentiable, which means that sudden shifts are unlikely. And therefore we can explore sort of the downs. The upside we get this smooth confidence span, a smoother process. The downside is, of course, if the process never suddenly change and then change, we will not be able to capture it perfectly. So here in the middle of January, we had a steep increase of number of deaths in UK. But as you can see here, something starts to happen. And as we gather more data, we can see here.
Can you explain the difference between the two pictures? Because I mean, what is on one and what is on the other?
So to the left is this simple model.
Oh,
which doesn't use a Gaussian prior. On the right is with you have Gaussian prior. And although it's sort of hard to see from what is reported so far, you can sort of see the true data that there is a shift. It suddenly broke. And here in the pure prior model, which doesn't care anything about the dependence, it already started to see this, that there is something going on here, while the Gaussian model says straight up, because the path is very clearly indicating that it goes straight up. And as you see, it still is sort of starting to fall, but the model doesn't see it. This model capture is fine. And here you can see that the confidence band is not that extreme for the British data, and that is because they are much more better at reporting the Swedish data. So you quite quickly have a good reasonable estimate. So you don't really need as much the Gaussian process. But here you can see now that slowly the Gaussian process start to see, okay, there is actually something happening, and starts to capture this eventually. But it is off while the other model already had seen this for quite a while.
So is it in this latent Gaussian process, you assume matrix covariance, right?
Yeah.
And it's sort of, this is the effect of that, right?
Yeah, precisely. I mean, exactly. So if you look at the data here, it is a smooth process, meaning that the past things does not change very quickly. And this is an outlier event in some sense, right? In the sort of spatial, in the temporal setting. This is a sudden shift, but you don't see this sudden shift otherwise. Like it was going straight up, very high increase, and all of a sudden it just collapsed and went the other way. It's almost like a discontinuity in the derivative. But if you looked at the data we'd fitted so far, it would definitely find a more smooth version. So it was a very unlikely event. And there the process wasn't able to capture it, but this actually was quite nicely able to capture it because the data indicated it rather quickly.
Because it didn't remember simply.
No, yeah, precisely. It just seems reporting. They are independent, so it doesn't care. But you could see it in the data. But when you you pay the price of assuming that the data is dependent, and then you try to capture this behavior, and then you get the change point, then you will do worse predictions. Yeah, and we see here. Let's see. Yeah, but in the end, it takes a few days for it, and then it sort of starts to capture the behavior. So, but that sort of goes back to your question, Gosha, that it will fail in the beginning. I don't know how much we'll talk about this, but yeah, we also have we use these scoring rules to measure how well we predict. And this is the Swedish data for the second wave. And what you see here, although not perfectly, is that we take Christmas break in Sweden, and there all of a sudden, and they had the same, we see the same, but a little bit less in the UK, is that once there is a Christmas break, the reporting goes down. The reporting slows down, right? And if the model does not perfectly take this into account, we will get an underestimate of the number of deaths here also. So it's very important there to keep these things flat. So here we got very poor prediction around early January, late December, and this is due to the Christmas break. But otherwise, it's rather stable.
Can you say something about the magnitude of CRPS here?
No. I didn't want to do a little bit of this, but sort of CRPS is sort of tricky also in the sense that, well, yeah, I should say that the small values are good. No, big values are good, right? 0 is the best. There is plus and minus. You can never decide which is the way to use. But there is an issue which I'm going to talk about at the Nordstat about CRPS, that it is, if the variance of your predictor goes up, the expected CRPS goes up also, which makes the result a bit more tricky to interpret. But this very large outliers is due to the fact of Christmas break. But there is a natural that they should go up a bit because we are in the middle of the values number that were highest here also. But that's I don't want to go into that. So Gaussian, regarding sort of the how well it works, sort of if we do it for everything, this is Adam's. That's why it's much nicer figures than previous ones. So it's not me who have done it, and this is sort of what he presents on his homepage these days. So here is the number of confirmed deaths in COVID Sweden. Here we see our little prediction at the very end. And here you can sort of see here the colors depends on which day it was reported, at what lag, right? So red means that it was reported the same day. And you see here, Chris, you see that they stopped doing this around here. So there they changed the pattern, but also you can see that the proportion of blue compared to yellow, for instance, which is 5 to 6 day, is increasing. So here it was a little, but here it's the same. And here it's much more. And here you have the really long delays is due to the Christmas effects. So here we sort of have pictures describing the behavior we see here. And also you see that here they were reporting every day, and here they start to report fewer and fewer times. At least the picture is positive, that the cases don't go down. And you can see here that we don't have, unlike the UK, we don't have a sudden shift in the model. So here a smooth Gaussian process would fits, and it actually does fit much better because there is no sudden break. Whereas if we look at the UK data, here where we have data accessible, this is where there is a sudden drop off. It's very sharp and switches signs very sharply. Whereas you can see in Sweden, there is more of a going on to a plateau. And this is very hard to handle for a Gaussian process, unless the sort of process is rather rough, meaning there's few times differentiable. And you can also see that the number of blue here, the proportion of blue is very small. So blue is 7 to 13 days. Basically, you know how many there are after 7 days. Whereas in Sweden, we definitely don't. So the reporting is much more stable in the UK. And yep, that's what I had to say. Thank you for your attention.
Thank you very much, Jonas. Are there any questions from participants?
Well, I have a question, maybe not related to your model, but the way it is reported still in Sweden, that on the given day, there's sudden peak that is disappearing later on. What is that? I mean, it's